Let me define the electromyography force, or EMG. So EMG is defined as the study of myoelectric activity. And what EMG actually measures is action potential. Then there are 4 steps in action potential, which are resting membrane potential, polarization, and depolarization, the repolarization. Let's take a look at each step. And polarization and resting membrane potential. Let's take a look at these two together because they occur when no stimulus arrives. That's why. And then let's take a look at the structure of muscle fiber or muscle cell membrane to better understand these two concepts. So we have a sarcolemma here, this muscle membrane. So intracellular means inside of the muscle membrane, and extracellular means outside of the muscle membrane. And then we have a sodium and potassium pump here, and then sodium channel, and then potassium channel. And then when no stimulus arrives, as you can see here, this pump is very active. So the sodium can move out of the cell and potassium can move into the cell. And then sodium channel is closed and potassium channel is partially open. So the potassium can move out of this cell. And then polarization means the state of minus ion and plus ion being inside and outside of the membrane respectively when no stimulus arrives. That's called the polarization. And then resting membrane potential is defined as difference in resting voltage between inside and outside of the membrane during polarization. And then we have here value of resting membrane potential here, so minus 90 millivolt here. Here minus value means so we got lower inside the voltage relative to outside the voltage. That's why we got the minus the resting membrane potential during polarization. Then why do we have a plus ion in extracellular and then minus ion in intracellular? There are multiple regions here, but just take a look at two primary regions. So we have a different concentration of sodium potassium across this membrane, that's why. And then due to the potassium permeability, that's why we got the plus ion in extracellular and then negative or minus ion in intracellular. Depolarization and action potential. And these two occur when stimulus arrived. So the sodium channel is now open and potassium channel is closed, which results in the influx of sodium across this membrane. So as you can see here, again, when stimulus arrived, it will result in the influx of sodium across this membrane. Okay? This step is called depolarization. And then depolarization keeps propagating sodium in both sides, this side and then this side. Then this propagation leads the sodium channel to be open. And then action potential is defined as the difference in the voltage between inside and outside of the membrane during depolarization. And then the value of action potential during the depolarization is around 120 millivolt. Then we got here plus value here, which means we got higher inside the voltage relative to the outside the voltage. That's why we got the plus or positive action potential value here. Repolarization and action potential. Repolarization is the step of getting back to polarization to be ready for receiving another stimulus. So during repolarization, the sodium channel is closed, but potassium channel is fully open, which results in the outflow of potassium from the inside of the cell. This step is called repolarization. That's why you can see the potassium located in outside of the cell, and then sodium is located inside of the cell, which looks different from initial polarization. And this is due to the outflow of potassium. So we have to rearrange sodium and potassium to get back to the initial polarization state. So we have active sodium potassium pump here, which rearrange sodium potassium like initial polarization state. Let me visualize 4 steps in action potential. Number 1, here polarization. We have number 1 here, so when no stimulus arrived. And then 2 and 3, these steps are depolarization. And then number 4 is the repolarization. And then number 5, from here to here, is action potential. And this is what the EMG actually measures. We need to understand the physiological origin of EMG signal. So here we have action potential. So AP represents action potential. So this is coming down from the central nervous system, which means this is a motor neuron here. This part is the terminal end of this motor neuron. Then we have a space between this motor neuron and muscle fiber, which is called synaptic cleft right here. And then we have a specialized region on muscle fiber membrane, which is a motor end plate. And then this action potential result in the release of acetylcholine stored in the synaptic vesicles. So green dots here, this is acetylcholine. Okay, so released acetylcholine can migrate across this synaptic cleft, and then this released acetylcholine can bind with motor end plate on the muscle fiber. This binding will trigger another action potential. That's the muscle fiber action potential. So I can call this MFAP, muscle fiber action potential. And then this action potential then can move into the muscle fibers through T-tubule. Once this action potential move into the muscle fiber, that results in the release of calcium stored in sarcoplasmic reticulum. And then this release calcium then binds with troponin, which cause tropomyosin of this actin. And then again, this binding of calcium and troponin will cause the tropomyosin of this actin, which result in the cross bridges of the head of myosin and the actin. Okay, motor unit action potential. Before we take a look at the motor unit action potential, let's take a look at motor unit first. Motor units consist of single motor neuron and muscle fibers innervated by this single motor neuron. So this is an example of motor unit here. So we have a central nervous system, and then we have a multiple motor neuron here. Each motor neuron can innervate a number of muscle fibers. So it can branch out and innervate muscle fibers. And then here innervation ratio, which means the number of muscle fibers per motor neuron. So 1 to 10 or 1 to 100, even more than that. But this innervation ratio is based on the mechanical function of the motor neurons. Okay, now we can define motor unit action potential. So motor unit action potential can be defined as the sum of electrical activity of all muscle fibers activated within a motor unit. So here this figure can help us better understand the motor unit action potential. Number 1 here. So motor neuron action potential, which is coming from the central nervous system. So this motor unit action potential can release acetylcholine stored in synaptic vesicles, as I mentioned earlier. And then number 2, the motor end plates we here. So this release acetylcholine arrive at the motor end plates on the muscle fiber membrane. and then by the electromechanical process, a muscle fiber action potential is produced and propagates along the length of the muscle fibers. This is number 3. And number 4, motor unit action potential, which is the sum of all muscle fiber action potential activated by one motor neuron. Then we can get this motor unit action potential. Finally, we can measure this motor unit action potential using the EMG. Number 5. This slide shows what factors can affect the motor unit activation. The motor unit activation can be affected by motor unit recruitment and firing rate and synchronization. And then motor unit recruitment means the number of motor unit recruited. As you can see here, in a single muscle, you can have a mixture of different muscle fiber types. SO, FOG, FG. SO means slow twitch oxidative. The FOG means fast twitch oxidative glycolytic. And FG means fast twitch glycolytic. Again, in a single muscle, we can have a mixture of different muscle fiber types. Smaller muscle will be used first. The larger muscle will be used later. The firing rate means how frequently motor units are activated, and synchronization means 2 or more motor units fire simultaneously. So EMG signal. EMG signal is composite electrical sum of all of the active motor units. Then the magnitude of motor unit action potential can be affected by innervation ratio, then depth of the muscle fibers. Innervation ratio here, we have 2 motor neuron here. So this one can innervate these muscle fibers, whereas this motor neuron can innervate only these muscle fibers. And this innervation ratio can affect the amplitude of motor unit action potential. And also here, depth of muscle fibers. We have 5 different muscle fibers here, from 1 to 5. And in this figure, the number 5 is the deepest muscle fibers among these 5. That's why we got the lowest, the magnitude of this action potential value here, which means depth of muscle fibers can also affect the motor unit action potential. And then here, EMG signal means, as I mentioned earlier, composite electrical sum of all of the active motor units. So that we have to add all the motor units action potential. We have 2 motor units here, so alpha A and alpha B. And then this signal is the motor unit action potential obtained from this motor neuron. And then so MUAPP, this motor unit action potential obtained from this alpha B motor neuron. And then we have to add these 2. This is what actually EMG measures. Let's take a look at how to record the EMG signal. An EMG amplifier is actually required for recording EMG signals. And the EMG uses it's called differential amplifier. And what it does is that it records electrical differences between 2 recording electrodes and attenuate any signal that is common to the 2 inputs. And there are some considerations to be made in the EMG amplifier, such as monopolar versus bipolar recording, and common mode rejection ratio, and gain, and etc. But we're going to take a look at only these 3 considerations in this chapter. The EMG signals can be recorded using either a monopolar or bipolar recording. Bipolar recording is also known as signal differential recording. Let's take a look at monopolar recording first. One electrode is placed over the muscle, and a second one is placed at an electrically neutral site. It's also called ground, such as bony prominence. And generally, this monopolar recording generates low frequency responses. and less sensitivity than the bipolar recording. And then this is often used during the static contractions or clinical investigations using needle electrode. Then this would be a poor choice for measuring non-isometric contractions. And then this is example of, again, monopolar recording. We have one electrode placed over the muscle, and then the other one, second electrode, is placed at the, it's called neutral site or ground. Bipolar recording, and this recording is more stable than the monopolar recording during the non-isometric contractions, so that this is more common compared to the monopolar recording. Then in this bipolar recording, two electrodes are placed over the muscle, and then the third one is placed at the neutral site or ground. Then this bipolar recording uses a differential amplifier that records the electrical difference between the two recording electrodes. Thus, any signal that is common to these two inputs is attenuated. This concept is called common mode rejection. So this example of bipolar recording, we have two electrodes placed over the muscle, and then the third one is placed at the neutral side or the ground. Let's talk a little bit more about common mode rejection ratio, which is defined as the extent to which signals common to both inputs are attenuated. So this ratio should be as high as possible. Okay, there are two figures here. Okay, this is a monopolar recording, the bipolar recording. So we have one electrode placed on the muscle and one on the neutral side or ground. Once we collect the EMG, the data from the muscle, and the EMG signal contains both EMG and hum, which is a noise. But since this is monopolar, so we cannot attenuate the noise signal here. However, the bipolar recording, so we have two electrodes placed on the muscle, and then one on the ground. And this is from the first electrode, and this is from the second electrode. And the hum is the common to both electrodes, so that this hum can be attenuated using a differential amplifier in bipolar recording. That's why eventually we can get the typical EMG, the signal pattern, which does not contain the hum. Now, common mode rejection ratio is often expressed as logarithmic ratio, and then the units of this ratio are decibel. So if this ratio is equal to 10,000 to 1, which means all but 1 over 10,000 of the hum will be rejected, then this ratio will be equal to 80 decibels. In good quality amplifiers, this ratio should be 80 decibel or higher. Then where is the common mode coming from? So typically this mode is coming from the radio frequency and line activity from electrical outlets or lights. And then this common mode is typically 50 to 60 Hz directly in the frequency range represented by the EMG signals. Gain is the ratio of output voltage to input voltage. The raw EMG signal is between a few microvolt and 2 or 3 millivolt and amplified by a factor of at least 500 to 1000. Ideally, the gain should be set in such a way that the amplitude of the signal is matched to the range of AD converter. Electrode types. For surface EMG, electrode is placed on the skin over the muscle. So these surface electrodes are commonly used for clinical application, but this is a limited use in recording activity from deeper muscles. Because as I mentioned earlier, these electrodes are placed on the skin over the muscle, that's why. So that is difficult to discern if the signals arise from underlying muscle or an adjacent muscle. which means crosstalk. For needle EMG, a needle is inserted through the skin into the muscle. That's why the needle electrodes are often used to monitor the activity of one or more individual motor units rather than EMG activity of the composite muscle. So electrode placement. Correct electrode placement is very important, so that the electrode must be placed in a position from which action potentials from the underlying muscle fiber can be recorded. And the orientation of electrode with respect to the muscle fiber is also very important. If the electrode is not placed parallel to the muscle fibers, then the amplitude of the signal may be reduced by as much as 50%. So what can influence the EMG signal? First, electrode. Okay, there are different types of the electrode, as you learn. Surface electrode or needle electrode, or configuration, like a monopolar versus the bipolar. Then muscle length can also influence EMG signals. A decrease in muscle fiber conduction velocity with muscle lengthening. And then the amplitude of the action potential declines with increasing muscle length. That's why the electrode and muscle length can influence EMG signal. And muscle depth can also influence the EMG signals. So action potential decays rapidly as the distance from the recording electrodes increases. And then we can have a biased EMG signal due to the muscle depth. For example, deeper muscle fibers can have more slow twitch recruited at lower forces. And then more superficial muscle fibers can have more fast twitch recruited at higher forces. So you can have biased EMG signal due to the muscle depth. Crosstalk can also influence the EMG signals, and then crosstalk can increase with the size of subcutaneous fat layer, such as gluteus maximus. This is example of crosstalk, and then this figure is the cross-sectional view of mid-thigh muscles. And then we have 7 electrodes placed on this mid-thigh segment. So 1, 2, 3, 4, 5, 6, 7. And then we have an arc here. Each arc represents the zone of pickup of each electrode. And then as you can see here, there is overlapping, okay, here, here, here. There is an overlapping zone between adjacent electrode that will result in some crosstalk, which means this overlapping area will generate some crosstalk between adjacent muscles. It's time to talk about how to analyze the EMG signal. Two important characteristics of the EMG signals are amplitude and frequency. And amplitude is an indicator of the magnitude of muscle activity occurring due to the increase in motor unit recruitment and firing rate. And the frequency is also affected by the motor unit recruitment and firing rate. And then there are 5 major amplitude variables here. Okay, let's take a look at the peak-to-peak amplitude, which means negative peak to positive peak amplitude. So if you have an EMG signal, as you can see here, the negative peak to positive peak, this is a peak-to-peak amplitude. And this is particularly useful for synchronous signal called M wave and H reflex, which is evoked by the delivering a low intensity electrical stimulus to the peripheral motor nerve in an effort to activate only the primary or spindle afferent. Okay, the next one is average rectified amplitude, which is right here. Okay, this one. Then the normal EMG signal is an alternating current signal in both the positive, the negative voltage directions, as you can see here, positive and negative directions. And then unless there is some voltage offset in the signal, the mean of the signal will be equal to 0, which is not valid indicator of the EMG amplitude. So that you can convert the negative signal to the positive value. That's the average rectified amplitude. Next one is a linear envelope. So this is this one, okay, this figure, the linear envelope. And then an estimate of volume of activity can be obtained using a linear envelope. And it can be obtained by passing a low pass filter through the full wave rectified signal. And then the cutoff frequency is generally set at 10 Hz. Next one is called integrated EMG. So this figure, integrated EMG, which means total accumulated EMG activity for a chosen time period. An integrator is an electric device that sums activity over a period of time so that the total of accumulated EMG activity can be computed for a chosen time period. Next one is a root mean square amplitude. This one does not require full wave rectification. So this equation for root mean square amplitude, and then here EMG, the value of EMG signal at each moment of time t, and then capital the T, this will represent the duration of the analyzed signal. So you can use this formula to obtain root mean square amplitude. In addition to the EMG amplitude, EMG frequency can also be analyzed. Typically, there are two ways of analyzing EMG frequency. The first one is to define the turning points and the zero crossings. And this is one of the simplest ways to describe the EMG frequency. And then we have here simulated EMG signals here. For turn points, this one is the number of turning points in peaks per unit time in the EMG. So if you have this EMG signal here, you can simply count the spike peaks. Okay, this one, and this one. That's why the black circle means the turn points. And for zero crossing, this is the number of the signal crosses the zero. So again, in this EMG signal, you can just simply count the number of the signal crosses the zero right here. So this is a square represent again zero crossing. You just count these numbers. Okay, this is the first way of describing the EMG frequency. The second one is identifying the mean and median frequency. And then power spectrum is often used to describe the EMG frequency characteristics. In general, surface recorded EMG frequency is positively skewed, as you can see here. And the median frequency is approximately at 100 Hz, and mean frequency is approximately at 112 Hz. And then this is an indicator of changes occurring in muscle fiber conduction velocity. The mean and median frequency, these are often misinterpreted or overinterpreted. For example, if we have an increasing frequency, does that mean more active fast-twitch motor units? No, not always. So we can have an increasing frequency from higher firing rate for slow-twitch motor unit, also activation of muscle fibers with higher conduction velocities, or decreasing motor unit synchronization, and additional activation of synergist muscles or other possibilities. And one more example here. Okay. If you have a decrease in frequency, does that mean we got the increased motor unit synchronizations? It's not always. We can get a decrease in frequency from the decrease in total number of active motor units, or a decrease in motor unit firing rate, or a slowing of conduction velocity or other possibilities. That's why, again, as I mentioned, we should be careful of interpreting mean or median frequency result. Mean and median frequency during dynamic contractions. Mean and median frequency, these two are difficult to use during dynamic contractions because we assume that the signal is stationary. And then the stationary assumption is well met during isometric contractions, particularly for short time intervals. As a result, interpreting the EMG frequency during dynamic activities requires a particular. Let me talk about normalizations of the EMG signal. So why should we do EMG normalization? So EMG signals are needed to be normalized to compare the EMG signals between trials when electrodes are reapplied. For example, the data collection on different days. Also, to compare EMG signals between different muscles and different individuals. Okay, this is why we have to do the EMG normalization. There are different ways of normalizing the EMG signal. First one is maximal voluntary isometric contractions. So I can say MVIC. So for MVIC, the participants are asked to perform a maximal voluntary isometric contraction before actual data collection. And then the EMG value collected during the actual data collection is normalized to the MVIC. Usually, the normalized EMG value is expressed as a percentage of MVIC. However, MVIC, this normalization may be somewhat inappropriate when the investigation requires dynamic contractions. If then we can use maximal voluntary dynamic contraction or submaximal voluntary dynamic contractions. For maximal voluntary dynamic contractions, MVDC, we can use peak EMG, the value from the MVDC trial, with the same muscle action as the task. The force of maximal voluntary dynamic contractions, which is similar to the maximum voluntary dynamic contractions. So we can use peak the EMG from a submaximal the voluntary dynamic contraction with the same muscle action as the task. And also you can use a mean or peak value of the EMG signal so that the ensemble average mean or peak EMG from the task, these values can be used for EMG normalization. Let me give you 2 examples of measuring MVIC. Okay, these are pectoralis major. How to measure MVIC of pectoralis major. So there are 2 different ways of measuring the MVIC of this pectoralis major muscle here. So prone position and then push-up position. So for this one, the prone lying position would best be performed with a fixed long bar, and then push-up may work as an easy to set up alternative. The both positions should be performed in 90-degree elbow positions. So participants are asked to exert as much force as they can for measuring the MVIC. And this is how to measure again MVIC of gluteus maximus. Again, this is another example of measuring MVIC. It should be performed both in extended and flexed knee position with slightly outward rotated leg. Okay? And then again, the participants are asked to exert as much force as they can. And the hyperextension, this angle position is around 20 degrees. This is very important. Sometimes the no normalization of the EMG signal is necessary. For example, frequency analysis of the EMG signal. For this frequency analysis, the shape of power spectrum and frequency, these are more important than the EMG normalization. That's why we can simply use the frequency, mean or median frequency. Okay, if then we don't have to do the EMG normalization. And then the time of the initiation of the muscle activation. Okay, the initiation activation is usually identified from the raw EMG signal. That's why we don't have to do the EMG normalization. And also, if you have a paired sample design, then you don't have to do the EMG normalization. Because amplitude comparison from a given muscle between conditions within an individual in the same session under the same experimental conditions without changes to EMG electric setup. If then we don't have to, again, the EMG normalization. This is a per sample design. But comparison of muscle activities between the muscles and individuals is not valid. Okay, so we have to be careful of interpreting the data. Okay, we are done with the overview of EMG. That you learned many concepts here, so that you need to understand the concepts before you collect the data using EMG, or before you develop a study that requires you to use an EMG.